Machine learning is the field of study that gives computers the ability to learn without explicitly being programmed. Two different ways to teach a computer are supervised learning and unsupervised learning. In supervised learning, we are given a dataset and already know what our correct output should look like. In this type of learning, problems can be categorized into regression and classification problems. In a regression problem, we are trying to predict results within a continuous output, for example, predicting the price of a house based on its size. In a classification problem, we are trying to predict results in a discrete output, for example, given a picture of some animal, determining if it's a dog or not a dog. In unsupervised learning, we're given a dataset and we don't know what our correct output should look like. Instead of having labeled examples to learn from, the algorithm explores the data on its own, identifying patterns, relationships, or clusters without guidance. For example, given a large collection of articles, using this type of learning, we can analyze text and automatically group similar articles together, revealing patterns or maybe themes without any predefined labels. To represent our model, we'll use symbols like x to the power of I for input and y to the power of I for the output, so the pair xi, yi represents the ith training example. Using this dataset, we want to create a hypothesis, which is a function that takes an input x and gives us a good guess for the output y. A function for measuring how good our hypothesis is called the cost function. The cost function is like saying how wrong are we on average. It calculates the mean of the square differences between our guess and the real outcome. This is known as the squared error or mean squared error function. This function helps us figure out how much we need to adjust our guess to get it right on the next time. Let's see how the cost function helps us with linear regression with one variable. Let's say you have a bunch of points on a graph and you want to draw a straight line that goes through these points in the best way possible. The idea is to find θ0 and θ1 so that the average squared vertical distance from the points to the line is as small as possible. This will minimize our cost function. In a perfect scenario, the line would go exactly through every point and the cost would be 0. But usually nothing is perfect and we'll most of the time end up with something like this. Finishing yesterday's episode, we had our hypothesis and we had a way for measuring how well it fits into the data. Our goal is to minimize the cost function, and that way we can know that our hypothesis makes good guesses. That's where gradient descent comes in. Gradient descent is an optimization algorithm that helps us improve our hypothesis by minimizing the cost function. A simple way to see the value of the cost function for each pair of θ0 and θ1 would be putting θ0 on the x-axis, θ1 on the y-axis, and the cost function on the vertical z-axis. Looking at this graph, our goal is to get to the very bottom of the graph. Starting from randomly chosen θ0 and θ1, we check the slope of the landscape at our current location and we use that to walk downhill from our starting point until we reach the bottom. Our step size is affected by two things: the slope of the landscape. The steeper the landscape is, the bigger our step, and the learning rate, alpha. Too big and we might overshoot the minimum, too small and it will take us forever to reach the minimum. Mathematically, alpha is the parameter in which we multiply the partial derivative of the cost function for updating both θ0 and θ1 simultaneously. Something you might have noticed is that changing the starting point can change the final θ0 and θ1 we reach at the end of the algorithm. For example, starting from this position, we might end up at a point which is obviously not the very bottom of the pits in our graph. The good news is that in our case, with linear regression, there is only one lowest point, a global minimum on this landscape, which means that gradient descent will get you to the lowest point. It doesn't matter your starting point. If you like my summaries, I invite you to follow my Zero to Hero machine learning series, where I upload daily about my progression in AndrewNg's course.